Hi, so today we're going to talk about two proportion z-tests. And let's take a look at this problem as a way to explore them. There's a driving school owner, and he believes or she believes that instructor A is more effective than instructor B. And we read a little further, we see that out of the 100 students that are coming into class, they're randomly assigned to two groups, each of size 50. One group's going to be taught by instructor A, and the other group's going to be taught by instructor B. And what we see next is what they was observed. We notice at the end of the course, 30 of instructor A's students had passed, while 22 of instructor B's students had passed. It's tough to read that, so I'll just erase that part for you. So the question is, does that evidence somehow that instructor A was a better teacher? And so this is a classic example of a two proportion z-test. So how do they start off? They start off where you define your parameters. So we're going to say let P sub A equal the population proportion of students in instructor A's class that pass. Right? So of all the students that instructor has ever taught, what is the proportion of them that pass? And we're going to compare that to P sub B, which is going to be the population proportion of students in instructor B's class that pass. And this seems like a reasonable way to compare the two. Question is a big enough difference here, say 30 out of 50 versus 22 out of 50, to say, hey, instructor A is really better. So let's give those things names, this 30 out of 50 proportion. That's called P hat sub A, the sample proportion of instructor A students who passed. And it was 30 of them out of 50. You divide that, you get 0.6. And we're comparing to that sample proportion to P hat sub B, which was, I'm forgetting now, if I look at the previous page, it's 22. So it would be 22 out of 50, which is really 0.44. So one thing you could say is, I think 0.6 is a lot bigger than 0.44, and therefore, you know what? I think this person's better, right? That's what you could say, because you think a difference of, what is it, 16% is a big difference, which is possible. I mean, it might turn out to be significant, but what we're going to do today is formalize that. And to start off your two proportion z-test, you always start by checking a couple of conditions. So number one, was an SRS performed for both, or was there a random assignment? And that was true. So you had two SRSs, that's good. The second thing you need to check is something called independence. This is the longest of the conditions to check. And to do that, you need to check that the population of students who had instructor A is greater than or equal to 10 times the sample size of students who had instructor A in this particular little study we have. So that's going to be 10 times 50 or 500. So we have to hope that that's true. And if that's true, then what you know is the standard deviation of P hat sub A is equal to this formula, the square root of P hat sub A times 1 minus the square root of P hat sub A. I'm sorry, 1 minus P hat sub A over, that looks like a plus there. Sorry, let me fix that for you. This should be a 1 minus, and then this should be the sample size of people in A. All right, so that would be some kind of number. I'm just going to not deal with that for now. The second thing you need to check is, again, you need to check for the population of people who have had instructor B. Is that greater than or equal to 10 times the sample size of students who had instructor B, which is also 10 times 50 in this particular problem, which is 500. And again, what that would do is, well, now you can do the standard deviation of p hat sub b, which would be the square root of p hat sub b times 1 minus p hat sub b over n b. And that would also be some kind of number. Now, if you were doing something called a two proportion z interval, then you would want to know what these two standard deviations are, and you would have to turn them into variances by squaring them, add them together, and take the square root to get the standard deviation of the difference. But since we're doing a two proportion z-test, two proportion z-tests are done assuming HO is true. And if we're assuming that HO is true, then that means that P sub A minus P sub B does equal 0. And that's the rationale by forming something called P hat combined, which means you take all the people who passed with either instructor and you add them together. So x sub A plus x sub B, the number of people who pass with instructor A's class, add it together with the number of people who pass instructor B's class, and then you divide that by the total number of people in both samples. Now, why are you doing this? You're doing this because if the two proportions are equal, then in essence the instructor doesn't matter, and you're just finding what's the total proportion of people who passed. So if we add them together, it's 30 pass in A plus 22 in B over 50 plus 50. So that looks like 52 over 100, or 0.52. Okay, and now once you have that, you're ready to find your standard deviation. So the standard deviation formula we're going to use is this. The standard deviation of p hat sub A minus p hat sub B is equal to the square root of p hat combined times 1 minus p hat combined times 1 over NA plus 1 over NB. Okay, so this is going to equal the square root of 0.52 times 1 minus 0.52, or 0.48, times 1 over 50 plus 1 over 50. And if we take the time to calculate that, we will get, this is what I'm getting 0.009984. I'm going to round that to about 0.01. Nice, easy number. Okay, so that's the goal of the second condition. The third condition is to check for normality. So how do you check for normality? In the case of proportions, you need to check the following. You need to check that n sub A times p hat sub A, and also that n sub A times 1 minus p hat sub A, both of these things need to be greater or equal to 10. And so if we take a minute to calculate this, we would get 50 times p hat is 30 over 50, or 50 times 0.6, you will get 30. That shouldn't surprise you. That's definitely greater or equal to 10. And if you did 50 times 0.4, you'll get 20, which is also greater or equal to 10. So that's part of it. You need to check it again for n sub b times p hat sub b, and also n sub b times 1 minus p hat sub b. So if we do that, we get 50 times 0.44, which is 22, which is definitely greater than or equal to 10. And then you'd have 50 times 0.56, which gives you 28. My claim is you shouldn't really be surprised. That's also greater than or equal to 10, but notice if you take the 22 and the 28 here and you add them together, you get the total of 50. It shouldn't surprise you because these 2% add to 100. Okay, since all four of those are greater than 10, what we can say now is that the distribution of p hat sub A minus p hat sub B is approximately normal. So it just takes a lot of time to get through those assumptions, but once you have them, you're good to go. Okay, ready? Next thing, draw a picture. So we draw our normal distribution. It's pretty close. We put HO in the middle, which in this case is uh, P sub A minus P sub B is equal to 0. And then we mark off our standard deviation. Our standard deviation of P hat sub A minus P hat sub B, we rounded it to 0.01. So we'll mark off 0.01 here, 0.02 here, and then here we'll go 0.01, 0.02, and so forth. Oh. So looking at this, it seems like the standard deviation is pretty small. And then I'm realizing there's one small thing we forgot to do. Um, Back here on this page, when I typed this standard deviation into my calculator, I made a small error. It didn't turn out to be this. I put an extra 0 here. So this needed to be 0.09, which would mean that this would round to 0.1. That's going to make a big difference for us when we draw a normal distribution. So these things here should have been 0.1, 0.2, negative 0.1, and negative 0.2. So, and that's because this standard deviation really is supposed to be 0.1. Okay, sorry about that mistake. Ideally, I should make them, but it happens. All right, so now we want to mark off p hat sub A minus p hat sub B, which we know was 0.6 minus 0.44, or 0.16, which lies somewhere over here. So I'll put it right there, 0.16. And since HA said that it was greater than 0, we should shade to the right. And we're just about there. We need a z-score now. So z is going to be our difference of 0.16 minus HO of 0 over our standard deviation, which is 0.1. So this turns out to be 1.6 standard deviations above the mean. And now it's time to get a p-value, which you can do by using a z-table or using something called normal CDF in your TA84 calculator. If you use normal CDF, you'll type in lower of 1.6, upper of a big number. The mean is 0 and the standard deviation is 1 because we're using a z-score. So I hit paste and enter here, and I get about 0.055, which surprisingly is really close to being significant, but doesn't quite make it. So what we say here when we're all said and done, we say since our p-value, right, which was equal to 0.055, is greater than alpha equals 0.05, we fail to reject HO. We did not find enough evidence to say that instructor A is significantly better than instructor B. So we really needed this p-value here of 0.055 to end up being less than 0.05. It didn't happen. It's really close though. So if you were suspicious, that maybe instructor A is a little bit better, you might have some justification for it because it's really close. It just doesn't meet our strict rule where we were saying we had to get less than alpha equals 0.05. So we failed to reject HO. We did not find enough evidence to suggest that instructor A is definitely better than instructor B. Thanks for watching.